Thank you very much. Thank you, Radu and Yura, for the invitation. It's always a great pleasure to be in Vienna. So, hello everyone. I will update about some recent progress about bilevel optimization. And bilevel, there are several types of bilevel problems. So just to be on the same page, I want to explain what I mean in this talk for a bilevel optimization problem. So we are dealing with bilevel that have two optimization problems. But we use the terminology of inner and outer optimization problems. So the inner is any composite optimization model, meaning it's built by the sum of two functions. What is smooth with Lifshitz gradient, and the other one is non-smooth, could be extended valued, meaning you can put constraints, non-smooth regularizer, and whatever you wish. And in general, we consider those optimization problems that the optimal solution set is multiple optimal solution sets, and therefore we consider another optimization, another objective function that we call omega, that we wish to optimize this additional function over all optimal solutions coming from the inner level. So we have the inner, the outer, and what we are actually interested is solving this optimization problem. So for the moment, assuming on the outer objective that it's a convex, I will put additional assumption on the outer objective later on, but it's all convex optimization. So if you go back to the 70s, the most classical approach to tackle bilevel optimization problems go back to the technique, the popular technique of Tikhonov, saying that we take the inner objective function phi, we regularize it with the outer objective omega, and we get a new optimization problem parameterized with a parameter epsilon. So actually, we have many problems. For any parameter, we have a new optimization problem. So the first result of Tikhonov is when all the involved functions in the story are linear, proving that if epsilon goes to 0, we can recover the bilevel optimal solution by solving this sequence of optimization problems, this classical optimization problem. There's no any more bilevel since we regularize the outer objective. Later on, it was extended to convex optimization, and even in a work of Michael and Paul, even for non-smooth outer objectives. And actually, Mangasaryan and Meyer actually show that you don't need to go all the way to the limit. They prove that there is small enough epsilon that if you know it, it will give you the optimal solution of the bilevel. But technically, obviously, in practice, we don't know what is this small enough epsilon, but they show you that you don't need to go all the way to the limit. But it's not very practical. So in general, as you see, this technique of Tikhonov is not exactly an algorithm. I mean, you can't implement it in order to solve a problem. It's kind of a conceptual idea how to treat bilevel optimization problems. So this technique was studied a lot in the literature since the 70s with many, many papers trying to develop algorithms to solve bilevel optimization problems. Most of those algorithms are based on the Tikhonov regularization. The first, what we called in this talk, direct algorithm, because again, the Tikhonov basic idea is not an algorithm. So direct algorithm in the sense that you can really apply it on a particular instance, is the work of Solodov from 2007 that actually take a sequence of epsilon k. At each iteration is apply projected gradient. You can also generalize it to proximal gradient, changing the epsilon every iteration. So if the epsilon satisfies these conditions, going to 0, but not too fast, he proved that this algorithm generates a sequence that indeed converges to the bilevel. So most of the work was done to prove convergence results. But rate of convergence was luck. So in this talk, I mostly focus on algorithms that have certain rate of convergence guarantees. Okay. Inner level, outer level. Yeah. No. Okay, so this is what I said. There are several types of bilevel. So we need to distinguish. We don't have here two players. It's a kind of related, if you want to go to game theory, it's a follower leader. So you have only one player, one. No, this is exactly no. This is what people call the simple bilevel in the literature. Yeah, yeah. You don't. The inner optimal solution set is fixed. It's not parameterized by any vector. I mean, to say that I will clarify what I mean by level, but you're right. Okay. So as I said, we want to focus on algorithms with certain convergence rate guarantees for simple bilevel optimization problems. And the first work that developed an algorithm and proved a rate of convergence, going back 10 years ago with Amir, that we developed the MNG algorithm, minimal norm gradient method, that actually is an algorithm that builds two half spaces at each iteration, and then in the simple case, just take a projection on the intersection of two half spaces. One half space is related to the inner problem, the other one is related to the outer, and then we just compute the argmin of the outer, so you can think about the outer in the simple case, just norm square, so it's just projecting onto the intersection of two half spaces. And in this work, we proved that indeed this algorithm generates a sequence that converge to the bilevel. So you see there, we are not following whatsoever the technique of Tikhonov. We don't have any regularization here. We don't need to work with any parameters. We just solve directly the bilevel optimization problem. And we proved a rate of, on function values. Yes? Which? For the bilevel? Okay. I mean, in the general, this half space stick. What? No. Oh. Yeah. So Ogazo is it's all. Yeah, the motivation is Ogazo, but it's all just convergence. We were focusing on rate of convergence. Yeah. We proved in terms of the inner objective function on the sequence that actually the feasible sequence, we proved O of 1 over square root of k. So it's relatively a slow rate of convergence, yes. Yes. Yeah. 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 What? Okay. And so motivated by these results, we keep thinking about achieving better rates of convergence. And 3 years later, together with Shimrit, we developed another new algorithm that actually also based on algorithm that come from fixed point theory, an algorithm of Shu, that again discuss only rate, just convergence and in more general setting of fixed point. And this algorithm, again, as the previous one, it should be clarified that we are working with outer objectives that it must be differentiable and strongly convex. So you can think about norm square, and there are not many more beyond of that. And again, with Shimrit, also in the same setting of differentiability and strong convexity, we were developing a new algorithm that actually what it is doing is taking operation on the inner level. So it's a just proximal gradient. Remember that it's a basic composite model. Take a gradient step on the outer and then mix them. Take a certain convex combination between these two operations. Obviously, the parameter that you take the combination is a vanishing parameter. And indeed, we prove that in this setting, again, only in terms of the outer objective function, you can get a rate of 1 over k. So again, direct algorithm has nothing to do with Tikhonov that achieve a faster rate of convergence, but limited to the differentiable and strongly convex setting. So 2 years after, there are several other papers that were thinking about this optimization problem, thinking about improving a result. So this is an example for a work that still in the strong convexity case, but consider outer objective that is non-smooth. For example, it's very interesting to consider L1 as the outer objective. Again, in this setting, we can't, but non-smooth. So they prove an inner rate, only on the inner objective function, a rate of 1/2 minus epsilon. Epsilon is a certain parameter that is used in the algorithm, and this algorithm is based on Tikhonov regularization. So they use the regularization technique in order to solve the problem. Also, the other paper, also based on Tikhonov, they actually consider in the inner level variational inequality. Outer optimization, inner variational inequality. They also prove 1/2 minus epsilon, but they managed for the first time to prove some outer objective. So far, it was only on the inner. They proved that also the outer objective can have a rate of convergence. Again, you see that it's complement to 1/2 minus epsilon and epsilon. Epsilon is a parameter between 0 and 1/2. There are many other papers that develop new algorithm rates in different settings, distributed, online, stochastic, but can't go beyond the rate that that you see in this slide. So the main goal of the rest of the talk is to consider only situation that the outer objective is not necessarily smooth, and we want to improve the rates that obtain in this existing work. So together with my master's student, we developed a new algorithm that we call BiSG. And actually, the BiSG, you will see, can consider two settings of outer objective functions. Depends on the situation that you have with your application at end. So first case is that the outer objective has no special structure. So we just requires that the outer objective could need to be Lifshitz. That's all is needed. And then in this case, what we are doing, again, we are not following Tikhonov regularization. But what we are doing here, if you remember, the previous algorithm was average of the two operations. So actually here, what we are doing is a composition of the two operations. So first, we consider the inner objective function. It's a classical composite problem, so we apply one step of proximal gradient, take the result, and apply just a subgradient step from this point. Okay, so it's a composition of the proximal gradient operation of the inner level, composed with a subgradient step with respect to the outer objective. Composition of two operations, inner and outer. Okay? So this is to the case that you don't have any special structure on the outer objective function. Again, we can extend things that if you don't know the Lifshitz constant with backtracking and all this, what we call technicalities, I'm skipping it in the talk. The other setting, it might be that your outer objective function has a structure of another composite problem. Everything is convex. And in this case, we consider that omega is given the sum of two functions, sigma, psi, and again, the classical composite setting, that you have a smooth function sigma with Lifshitz gradient. Psi is not smooth, extended value. And in this case, again, the composition effect comes into a play, but here we just compose the proximal gradient of the inner with the proximal gradient of the outer, and we get the new iteration. Proximal gradient inner, then on the results, another proximal gradient step on the outer, and this is the next iteration. Okay? What is important to note in both settings of the algorithm, the step size is a vanishing parameter. And we have a vanishing parameter that depends on parameter of the algorithm, alpha. So alpha is any number between 1/2 and 1. Okay? So we have two variations of the algorithm. In order to prove results, we unify both of them into one algorithm, and we define the capital omega operation. So it could be either subgradient of omega if we are in the first setting, or the gradient mapping with respect to omega when you have the composite structure in the second setting. And you can always write the by SG as this algorithm. All right? Either omega define one of these two options. So first of all, we prove that this algorithm under these assumptions, again, everything convex, the two sequences generated by the algorithms are bounded. And in order to equalize to the results about the inner optimization problems, we show that the inner optimization can be solved in a rate of 1/k to the power of alpha. So remember, alpha is a parameter that you can choose to play in your algorithm, how the step size is vanishing to 0. And it's the alpha, again, it's 1/2 to 1. And if you take the extreme case of 1, you need to pay the price of ln k in the nominator. Okay, so it's, again, a method that has, in the extreme case, O of almost 1/k, like we had before. But what is interesting here, that is very important to note, that we are able to get simultaneous rate. At the end of the day, we need to remember that we are solving two optimization problems. They are not independent. So when you get rates on the inner and on the outer, and in several papers they, I think, misleading with that, you need to get the rate on the same sequence, because you have two sequences of the algorithm. If you prove rate for the inner on one sequence, the outer rate is on other sequence, so you can't work with both rates at the same time. So here we have a simultaneous rate for both the inner and the outer, and you see again the trade-off of alpha. So if you take alpha large, you get very fast in the inner level, but very slow in the outer level, and vice versa. But you have all the range of k to the power alpha and k to the power 1 minus alpha. But here, in comparison to the previous results, alpha is between 1/2 and 1, so it's improved rate over the previous result. For the case, again, for alpha equals to 1, we can even get an inner rate, but is very, very, very low. Okay, we can extend a little bit the results to improve the outer objective if we have some strong convexity, like in the first results that I mentioned. So we can get also simultaneous rate with some linear rate, again, only on the strong convexity part, meaning the outer objective. So we get, if you have strong convexity, you indeed get a better rate in terms of the outer objective function. Okay, so just to conclude, some numerical experiments, just to show that the new algorithms, we were trying the algorithm on a nice example from fake news classification. And what we have here is we consider as the inner objective function the logistic regression loss. So we have examples taken from this website of fake news. And we took the outer objective in order to be able to compare it to the other algorithms that I mentioned, that most of them assume strong convexity, but we wanted to have some sparsity promoting functions, so we took the elastic net with just random parameter here in order to have some sparsity. So this is the inner objective function, this is the outer, so it's indeed a strongly convex function. And we just run a bunch of algorithms in order to solve the bilevel optimization problem. So what we see here, on the left-hand side, you see that we only track the inner optimization problem. So it's time versus progress in terms of the inner objective, the function phi. And this algorithm is the big SAM, the algorithm with Shimrit that I mentioned. So if you remember that I mentioned this algorithm, said that we can apply it only on differentiable outer objective function. So technically, it cannot be applied to this outer, but even in this paper, we mentioned that if you have a non-smooth outer objective, what you can do is to apply it on the Moreau envelope of the outer objective, and we show that you can get, obviously, a lower rate, depends on the Moreau parameter. So technically, I'm a bit lying here, but since it's previous algorithm of mine, I allow to lie here. So it's not really solving the problem. So it solves the Moreau envelope of the outer objective problem. Okay, so it's not exactly fair comparison, but what we see here, I took two parameters of alpha. Remember that we have the parameter of the algorithm. So the red is 0.95, and you see that indeed when I'm increasing the alpha, I'm getting better and better rates in terms of the inner objective function. Obviously, it's gonna affect the rates that I'm getting in terms of the outer objective due to the rate that we proved that we pay 1 minus the alpha. What we see on the right-hand side, it's interesting because we compare, as I mentioned, it's important that we are solving the two connected problems. They are not two individual problems. They are connected. So here on the x-axis, we consider the accuracy that we are solving the inner optimization problem. So I take the gap to the optimal solution and take minus logarithm. So here, any digit, it means how much I close to solve the inner optimization problem. Meaning, if I'm going to the right on the x-axis, it means that I'm solving better and better the inner optimization problem. Meaning that you see if this short line, it means that it solved very badly the inner optimization problem. And actually, you see that some of the lines even not appear here because they didn't manage to get this certain of accuracy in terms of the inner level. The y-axis, we are measuring the omega. So remember that we want, in between the optimal solutions of the inner, we want to minimize the outer objective function. So how you read this plot, so you take a vertical line, and so this is the same accuracy in terms of the inner, and what you want from your algorithm is to have the line that is the lowest. The lowest means that is found the minimal value of omega. So in between, for example, if I take 1.5, the green is the best. But as you see, the green does not go that far in terms of solving the inner problem. So the red is solving the inner problem in a much higher accuracy, but then we are paying in the price of finding higher value of omega. So this you see the same phenomena for underdetermined, overdetermined, and that's all the 3 papers that I mentioned and other references, so thank you very much.